Hi folks, welcome back to another Lab in Theory video. This is the second video in a series of videos on machine learning applied to the MNIST database of handwritten digits. In the last video, we looked at how we can apply the isomap dimensionality reduction technique to extract some interesting features from the dataset, and in this video, we'll be using this same dataset and applying a KNN or K nearest neighbors classifier to the dataset and see how well we can do. Just a quick recap, the MNIST database of handwritten digits is a collection of 60,000 examples for a training set containing the digits 0 through 9, and then another 10,000 examples for testing. Each image is a 28 by 28 pixel image, and we will be loading this up using NumPy, scikit-learn, and analyzing the data in a Jupyter notebook. So let's go ahead and get started. I have my directory right here in my working tutorials MNIST folder. Let's ls real quick. We can see right here we downloaded the training labels and images last time because we were doing unsupervised learning. We didn't need the test set, but in this video we're going to go ahead and download the test set as well. So let's go ahead and do that. I'm going to copy the link. I'm going to wget, download that, copy the link to the labels, wget, download that as well. Once again, we have to gunzip these, so gunzip t10k images and then gunzip t10k labels. Now that we have these unzipped, let's go ahead and get started. So before we begin in our Jupyter notebook over here, let's understand what the K nearest neighbors algorithm actually does. So K nearest neighbors is the simplest type of classifier you can think of. It does the following. It takes a point and it computes the distance of that point with all of the other observations in the training data. And then it labels it, that new point that you have, let's call it our test point, into the same class as the nearest neighbor to that point. Now, the problem with that approach is that, number one, it's quite expensive. Every time we have a new point that we want to classify, we have to compute the distances between that point and every other point in the training data set. So it becomes expensive both in storage and in computation because we have to store all of the training set. Now, as I described it, it is also extremely sensitive to outliers. So I described it by saying we take a new point, we find the point that's closest to it in the training set, and we just classify it according to the classification of that point. It's extremely sensitive to outliers, and that's why people came up with K nearest neighbors. The idea is very simple. It extends on what I just described. It considers K nearest neighbors, and it basically does a majority vote. And the idea is that in this case, I want to classify a point. Let me then take a look at the nearest 2 points, 3 points, 4 points, and classify it accordingly. That's all you need to know about the nearest neighbors algorithm. And here it's implemented in scikit-learn. It has a number of different ways to compute the nearest neighbor trees, but we're just going to leave it to auto. And if you're interested, you can click here and read more about the nearest neighbor algorithms in more detail. For us, auto should be sufficient, and we'll just go from there. Now, let's go ahead and create a Jupyter notebook here. So I'm going to create a new notebook. I'm going to give it a title. I'm going to call this MNIST K-means tutorial. And just like the previous video, what we want to do is also use the gist that we used here to load up the MNIST database files, which are stored in a binary format. I'm going to click raw, and I'm going to copy this function right here. First, of course, I need to show you there are a couple imports we need to type in here. So let's import struct, import NumPy as np, import, and actually let's import some scikit-learn stuff too. So from sklearn, we will import neighbors, and let's import metrics as well. And we'll talk about what metric we're going to use in a little bit. Also import matplotlib.pyplot as plt. We're going to plot up some data and then use our magic here. So matplotlib inline. Let's go ahead and run that. What did I type incorrectly? Of course, it's matplotlib. Off to a great start. Okay, now let's define our function here, def read idx, run that. And now let's import our training data. So we'll go raw train, set that equal to read IDX, and this will be train images, and then let's go ahead and flatten this. So what I mean by flattening, we looked at this in the previous video, is that each entry in this raw train array, NumPy array, will be a 28 by 28 image. What we want to do is to flatten that. So we have 60,000 entries in our training data set, and then each entry will be a very long vector. It'll be 786 entries long, as opposed to being a two-dimensional matrix. We're just flattening it out. So in this case, we'll say train data, and we'll set that equal to a NumPy reshape. We'll take our raw train and then reshape this into a 60,000 by 28 by 28. I said 768, but just to be sure, let's do it that way. My arithmetic's pretty bad. Okay, the train label here, let's import that. We'll go read IDX and then train labels. And now let's import our test set. So raw test, read IDX, T10 images. Yes, that's what we want. Same thing, test data, NP, reshape, raw test. In this case, it's 10,000, and then it's 28 by 28. And finally, the test labels. We will read IDX, and then this is T10K labels. Let's run that, and great. Now, of course, we have a pretty giant data set of full of the digits from 0 to 9. I'm going to pick out 3 digits, 2, 3, and 8, because they look somewhat similar to each other, and I find that it gives us a nice, good, useful learning example. So to select that, I'll just create a mask. I'll say IDX. This will hold our indices, equals train label equals 2, or we want train label equals 3, or we want train label equals 8. Now, once we have our indices, let's define our x data. X will be our train data selected out by IDX. And y will be train label selected out by IDX as well. Finally, we're going to actually create our KNN classifier. Let's take a look at what options we need to provide it right here. Let's take a look. Nearest neighbors. There we go. The first thing we have to provide is the number of nearest neighbors, a radius, an algorithm. Again, we'll leave all of these to the default options, and we will set n neighbors to a number, let's say, I don't know, 3, for example. You're free to experiment with different values of this hyperparameter, the n neighbors, and see how the accuracy of the prediction changes as the number of neighbors that you take into consideration changes as well. So what we need to do to initialize the nearest neighbors is specify n neighbors, and it also provides a fit function here. There we go, fit xy. So we'll do that all in a single command. So let's go back here. We will say KNN, our classifier is neighbors.k nearest neighbors classifier, and we will say n neighbors equals 3 dot fit xy. Go ahead and run that. That's not going to take too long. Okay, now the real long step will be the next one. Let's define a new selector. So now we're going to actually filter, or rather mask out the testing data for the same digits and see how well this classifier does. So in order to do that, we're going to do the same thing. So test label equals, that's not label, equals 2, and then test label equals 3, and then test label equals 8. Next, we will also define our xtest data. That'll be equal to test data IDX, and then y true, and that will be test label IDX, and we will have y prediction, and that will be equal to knn.predict. So we will predict xtest. And I'm going to go ahead and run that. Now, this will take a little bit of time because, as I mentioned, we are actually going to do a little bit of a search and try to match each point in this vector from our test data to the nearest 3 points from the training data set. So we'll come back once this is complete. Okay, we're back in action. The KNN predictor has done its job, and the next step for us to do is to summarize the quality of the prediction of the three nearest neighbors classifier. To do that, we're going to generate a confusion matrix. If you've never heard of a confusion matrix or you're confused, fret not. It's actually described right here. It's a simple matrix right here that contains these squares, each one containing the predicted label versus the true label right here. So, for example, if we predicted a certain class and the actual class that we predicted is that same class, we will be along the diagonal. So a perfect prediction would give us numbers along the diagonal and zeros everywhere else. And this is, again, a great way to visualize the results that we got from our classifier. So in this example in scikit-learn here, there's actually a very nice function that will allow us to visualize it using pretty colors. So I'm going to go ahead and copy that. We will need to import itertools, but that shouldn't be a problem. Let's go ahead and import itertools, and then just paste this function right here. Run that, great, no errors. So let's go ahead and plot our confusion matrix. What we need to do now is plot, well, let's do this. Let's say confusion matrix equals metrics dot confusion matrix, and then we go y true, y predicted, and now we'll go plot confusion matrix, pass in the confusion matrix, and our classes are 2, 3, 8. And let's go ahead and run that. Great. So here's our confusion matrix. These are the predicted labels 2, 3, and 8, and these are the true labels. So let's go through this a little bit slowly and see if we can interpret the results. What this is telling us is that our classifier predicted the digit 2 for this column right here. Out of all of the data, 1,025 samples were classified correctly. So we predicted 2, and the true label is 2. We predicted 2 for 5 digits, which were actually 3s, and we predicted 2s 6 times for digits that were actually 8. So that's how you read a confusion matrix. As you can see, we did a pretty good job overall. The majority of the values were predicted, the digits were predicted correctly, and only a few were not. And what I want to do as well is turn a normalize on. That'll allow us to get a better feel for the overall statistics. So normalize true. There we go. So you can see we got a 99% accuracy with the second digit, third 99%, and 98% for the 8th digit right here. Now, the real question is the following. Which digits did the classifier get wrong, and why did it get it wrong? So in order to understand this question, what we will do is we're going to plot up a few digits. In this case, I'm going to define an index. Again, you're free to experiment with this and select out whichever digits you want, but in this example, what I'm going to do is I'm going to use np, so numpy where, and I want to select out digits that were predicted to be 2, but were actually 8. And I want to see what those digits look like. Do they look like really poorly written 2s, such that even a human would mistake them as an 8? Or is our classifier just terrible at doing its job? We will find out after this commercial break. Just kidding. So let's see. Y predicted equals 2, and the Y true equals 8. And then numpy where returns a tuple. We want to select out 0. That will give us the indices of all of the entries that satisfy this criteria, where the prediction is 2 and the truth is 8. So we'll select out those indices, and we will create a figure. So fig equals plt.figure, fig size. We will make it, I don't know, 5 by 30. We want to make it kind of long because we're going to plot up, well, whatever the unnormalized value is, that many images. In any case, let's write a little loop. So for I in range len idx, we want to define axis equals fig.add subplot And len idx 1, we'll have just one column in this case, I plus 1, and then image plot equals ax.imshow. We have to reshape. You know, it actually makes a lot of sense for us to refactor this out as a function because we're coding this up pretty often in the last video, this video, and probably in the coming videos, but hey, I'm just going to type it up again this time because why not? Reshape, we want to unflatten the array that we flattened earlier, so this will be xtest, idxi, and then we're just selecting out that row. And we also want to reshape that to 28. Whoop, not 29, 28 by 28. Next thing we'll do is set our color map. So just cmap equals plt.cm.get cmap, and then we'll use the grays color map. Then image plot dot set interpolation nearest. Haha, nearest neighbor interpolation when we're using nearest neighbors. Oh, that's so cool. Okay, great. plt.show, delete that extra row. Okay, let's run that. Okay, here are the digits. Let's see if we can identify a pattern. So this was supposed to be an 8, of course, but it was predicted to be a 2. It pretty much looks like an 8, to me at least. This is a solid 8, solid 8. I don't know, a snakehead, scorpion. This is just a blob, 8. I don't know. My opinion is that the nearest neighbors happened to misclassify these because, hey, just dumb luck. And it wasn't due to any particular knowledge, if you will, to use that word, that the nearest neighbor classifier extracted from the digits, the training set, and incorrectly applied it to the test set. It simply happened to be that, due to some random noise in the data set, these points lied closest to the digit 2, or the corresponding 2 digit, and they were chosen as such. Let's see. Anything else that we can add to this? I don't think so. So, yeah. So these are clearly 8s. They're classified as 2s. And I think the message, the takeaway from this is we need a better classifier, which of course we'll get to in the next videos. Again, if you like this video, please give it a thumbs up. If you really enjoyed it, subscribe and stay tuned for more videos where we look at the MNIST handwritten database. Thanks for watching. I will see you in the next one. Goodbye.